Alright, so today we'll be talking about convolution, which is a topic that is usually taught in a very non-intuitive way. It makes it hard to understand and we are all scared of it. So let's just introduce it. So here's convolution. But before we do that, let's define some things. So the impulse response. So the impulse response is just an easy concept. All it is the response of the system to an applied impulse. So let's write that down and then we'll explain it in 1 second in a more graphical way. So an applied impulse. So remember, an impulse. This is the Dirac delta function. Remember, an impulse is just a simple signal. Signal. It's an amplitude of 1 at 0, and then 0 everywhere else. 1, 2, all the way up to infinity. Same for the other side. That is all an impulse is, or same thing as a Dirac delta function. Okay, so what that means is that the impulse response defined to be h of n is just going to be the impulse, the response of the system to an applied input. So in other words, all this means is that, say you have an impulse, right? You have this function and you put it into an LTI system. So what you will get out is just the impulse response, right? The response of the system to an applied impulse. Alright, so now we can remember that for LTI systems, the impulse response gives a complete characterization of the system. Now we can know the response of the system to any input. And how can we do that? We can do that via convolution. And so let's write that. Alright, so let's talk a bit about convolution. So, convolution. So, what is convolution? Well, mathematically, what they teach you in class and don't get scared. As I say, I'm gonna explain this. So they tell you, well, convolution is if you have an input and you convolve it with the impulse response of that system, you're gonna get the output. And this is only for LTI systems, linear and time invariant systems. Correct? Okay, so now the more intuitive view of this is the following. Convolution is simply a mathematical operation that allows us to get the output of an LTI system to any input just and simply by knowing the system's impulse response. So let's write that. Okay, so now let's write the mathematical description of that mathematical operation. Again, I mean, looking into this, it doesn't really tell you much, but in a minute, we're gonna run over an example that is gonna really let you visualize what's going on. So let's just write that. Okay, negative infinity to infinity. Okay. Okay, so what is the meaning of this sum, right? So that's the question. Well, in reality, it is telling us that the output of the system is the sum of scaled and time-shifted versions of the impulse response. Scaled by x of k and time-shifted by minus k, right? So you got the impulse response shift by minus k and scaled by x of k right here. So let's write that. And this right here is a very important definition that you have to remember. We'll exploit this in a little bit when we run our example. So you have to remember that. Alright, so now we want to know what's convolution really doing. So say we have a signal and we want to apply this operation. So what's going to happen? So let's run the example. Because right, if it's supposed to allow you to know the output of an LTI system by just knowing the impulse response, then can we actually do that? Well, let's take a look. So say we have a system for which its impulse response is the following. So say we have a system with impulse response. So we denote the impulse response of just being h of n, and it's going to be here. 1, 0, 1, 2, 3. So you can see it's pretty simple. So just a little for you to remember. So remember that we got this when we applied an impulse. Just so you remember what this means. Okay. And say we also have an input signal that we want to put into the system. Which is, in this case, is going to be x of n. Is given by, start again real quick. Start. So now the big point knowing these two things, and that we have an LTI system, so how can we actually figure out the output of the system? That's the big question. So someone clever might ask, right? If we know what the response is to a single what the response of the system is to a single input, can we break up the input signal into several impulses and then apply them individually to the system? And then at the end we add them all up and end up with the response of the system is to the whole input? It turns out that's all convolution is. So let's write that out. So, so a clever way could be if we know what the response to kind of write that in blue. So it's like big. So can apply them to the system. Individually. So that's the big question. And then to know the output, all of those responses add. Turns out that you can. Yes, that's a big yes. Actually, this is what convolution is all about. Geez, that was not too bad. Alright, so let's actually do it with the signals that the signal and the impulse response that we graphed, plotted just a little bit. So let's actually do it. So let's take our input signal and break it up into shifted impulses. So we're gonna end that with 1, 2, 3. Where, just for convenience, we're gonna name this one to be x1 of n, which is simply just going to be 1 times an impulse, and then we're going to x2 of n, which is simply just going to be, so 1 times an impulse at 0 right here, and then we're going to have x2 of n, which is going to be 2 times an impulse shifted by 1. So an impulse shifted by 1 multiplied times 2. Alright, now x3 of n is going to be 1 times an impulse shifted by 2. So an impulse shifted by 2 and multiplied by 1. There we go. So now let's just write them out real quick. So 1, 2. So that's all it is. And for this one, so 1, 2. So it is for this one. So 1, 2, 3. That looks too good. Okay, so now we want to know what would the responses of the system be to these individual impulses. So let's write that. That's the question. And here is where the linearity and time invariance come into play, right? We told you that, you know, these are LTI system, but what's the problem? We never mention it again. Okay, here is where they become important. Remember, from time invariance I remember that the response to a time shift at the input system would just be equivalent to a time shift at the output. Alright, so that's for time invariance. What about, so that is time invariance. So you can already start thinking where that's gonna fit into place. Now let's talk about linearity. So from linearity for a linear system, so a scaling at the input is equivalent to a scaling at the output. Alright, so let's apply these rules. We'll apply these rules to make this problem seem very easy. So we take, for instance, x1 of n, which is just equal to the impulse this one is just an easy case. And then therefore the output is just going to be y1 of n, which is just going to be the impulse response, right? So we denote that by saying alright, it's not too bad. Now it gets more interesting when we talk about the other ones. When we say, what about x2 of n? Right, that was the scaled and shifted impulse. Well, now here is where the LTI concept comes into play, right? What is this? This is an impulse scaled by 2 and delayed by 1. For LTI systems, due to the linearity and time invariance, this is equivalent to an impulse response scaled and delayed by 1. Correct? So let's write that out. So y2 of n is just going to be scaled by 2 and shifted by 1. Right, so delayed, time delayed by 1. Okay, so now let's do x3 of n minus 2. So this is just any impulse. By 2. So actually let's recall. So we can say is equivalent by L linearity and time invariance. So an input scaled by 2 and delayed by 1 is equal to the output scaled by 2 and delayed by 1. That's the concept we are using. Can do the same thing for the input tree. So an impulse delayed by 2 is equivalent to the output, in this case the impulse response, delayed by 2. Alright, now let's draw the individual outputs. So we're gonna have 3. And so y1 of n was just the impulse response. So it's just -1, 7, 1, 2, 3, 4. Simple. And y2 of n was just equal to 2 times the impulse response delayed by 1. So 1, 7, 1, 2, 3, 4. Two, and then y3 of n, it's going to be equal to impulse response divided by 2. Maybe a little bit smaller. Alright, so now you can probably guess what's going to happen next. We're going to add all the individual outputs to the system to get just the complete output of the system to the input signal. So let's try that. Now we add all Alright, so when we add them all up, we're gonna end up with, so we add y1 plus y2 plus y3, and the resulting signal, it's going to be the output of the system. And so it's going to be -2, -1, 0. 2, 3, 4, 5. So we're gonna have for -2, 0, -1, 0. At 0, we're gonna have 1. At 1, we're going to have 2 plus 1 is 3. At 2, we're gonna have 1 plus 2 plus 1, which is 4. At 3, we're gonna have 1 plus 2, which is 3. At 4, we're gonna have 1. This is 1. At 5, we're gonna have 0. Alright. So now note, all we did here was that we said, well, now we're gonna add the individual outputs to create whole output of the system, which is just going to be h of n plus 2 h of n minus 1 plus h of n minus 2. So what is this? I mean, here's where it all comes into light, right? This is just IE a sum of scaled and time shifted impulse responses. So what is this? This is all convolution, right? So what is this? Convolution, which is the alright. And this is what we just did was the following sum. So just by taking an intuitive approach to this thing, just the way it should probably be taught, we just perform the following sum. This is the scaling part, and then the shifting of the impulse responses right there. So now we want to say we want to express the output in a more sort of generic form. In a better way. So we'll say, y of n is just going to be equal to an impulse response plus 3 times an impulse response divided by 1 plus 4 times an impulse response divided by 2 plus 3 times an impulse response divided by 3 plus an impulse response divided by 4. That's it. So what you did, so that is all convolution is about. That's it. That's convolution. Cool. So now there's all these approaches. You see, if the input signals or the impulse responses get more complicated, then you can't really take this approach, right? Well, this approach is the real way. This is the intuitive way that it was developed. You have to take, the flip and shift approach, the one that they teach you and they tell you that that's intuitive. It's not, And so for that one, there's the graphical approach, which is the flip and shift. And there is the mathematical approach. The graphical approach gives you a little bit less intuition, and the mathematical approach gives you basically no intuition at all. So, but they are faster, right? So maybe we want to do that. So let's try that. I'm gonna go fast over this because it's not that important, at least. I mean, this is what they teach you at your university, so you can probably just go over the slides of the professor. And it will tell you, you have to shift one of the signals, flip and shift one of the signals, and then what's the output you end up with. But it doesn't really tell you what convolution really is. But anyways, here it is. Though a bit less intuitive. So here's the recipe. Since it's kind of mechanic, as I said, I mean, it's not like you can figure it out by intuition very well. So just kind of several steps. So from both signals, you're gonna have x of n and h of n. You're gonna choose and you're gonna choose h prime of n to be the easiest one to flip, right? The easiest to flip. So step 2, you're gonna say first, so 8, draw h of k, or x of k, I'm sorry, and then step B, what you're gonna do is you're gonna flip and shift h. In this case, this is the h to determine h prime, i.e. h of n minus k. And this is done for successive values of n. For example, you're going to take n equal to -1, then go to 0, then go to 1. And if you can't figure out the pattern, then probably you keep going until you see the pattern and you figure out what the output should look like. So now, step 3, it's going to be now multiply y of n is equal to h of k multiply h of k multiply times h of n minus k, and remember that's prime for your values of n. So for the example that we provided, just like n equal to -1, 0, and 1, what you're gonna do is you're gonna say, so for example, y of -1 is gonna be x of k times h prime of -1 minus k, and you're gonna say, alright, now y of 0 is gonna be x of k times h prime of 0 minus k. Now you can say y of 1 is equal to x of k times h of 1 minus k. And then if you don't figure out the pattern, then you just keep going doing the same thing. And if the signal is finite, you can probably do it until you just start getting a whole bunch of zeros. So try to continue the pattern for different values of n. Finally, step 4 would be you just draw the resultant signal for all values of n. So Alright, so now actually let's work out the same example we worked at before, just to compare. So let's do the same previous example. So if you recall, what we had before was just signal here, signal here. One, 0, 1, 2, 3, that's 0, 1, 2, 3, 4. And then 0, 1, 2, 3. Okay. So remember, that was the impulse response that we had before. This is for n. And then 1, 4. Sure, just make it like this. Negative 1, 0. 1, 2, 3. Negative 1, 2, 1, 1, 2, 1. Alright, so step 1. So we will choose, remember, you have to choose the signal that is easier to flip. So to flip and shift. So we'll choose the x prime of n. The one that we don't flip is just x of n, so we leave it the way it is. And then h prime of n, we'll do the same thing. I mean, it seems like it's pretty easy to flip this signal right here, so we'll just keep it the way it is. No change there. Alright, for some signals, it is a lot easier to define the signal to flip to be the other one. So, yeah. In that case, you would do that. So now, for step 2, we're going to draw x of k, x of k. So step 2a, we're gonna draw x of k. So it's gonna be the same thing, it's just with the indices changed. So you're gonna have negative 1, 0, 1. With that red color there. Negative 1, 0, 1, 2, 3, 4. You're gonna have 1, 2, 1, right? Right, 2, 1. Now the index is k. Make that looks actually. Alright, so there you go for x of k. Now for b, so this is step 2b, you're going to flip and shift h for these different values of n. Okay, so you say for n equal to 0, you're gonna have h of 0 minus k, which is just going to be simple. It's going to be similar right here. Now I'm gonna draw it in a little bit. N equal to 1, it's gonna be h of 1 minus k, which we have to factor out if we want to plot it. It's gonna be minus k minus 1. So we time reverse it and then we delay it. And then we're gonna draw that a little bit. And then for n equal to 2, so we're gonna try it for 4 different values of n. It's going to be h of 2 minus k, which is equal to h of minus k minus 2. Correct. And finally, we're gonna have n equal to 3, and hopefully that's enough to figure out what's going on. Minus k minus 2. Alright, so now let's draw them. So we're gonna put it -3, -2, -1, 0, 1, 2, -2. So just basically time reverse. That's it. And then for n equal to 1, we're gonna have, so again, -3, -2, -1, 0, 1, 2. We're gonna have time reversal and then a delay of 1 unit. So it's gonna start here. That's it, simple. That's 1. And then for n equal to 2, again time reverse, but then a delay of 2 units. So -2. So it's gonna start at 0. Okay. Remember, this is all k axis. And finally, the last one starts on -2. It's at 4. Starts at 1, 2, 3, something. This one. Okay, so now we proceed with step 3, which was simply, we multiply and sum. So that was just multiply and sum for all the values of n individually. In this case, it will be from n all the way up to 3. Right, so we're gonna say, okay, y0 is equal to x of k times h of 0 minus k, 0 minus k, right? And remember, this is n right here, and that's basically just going to be 1, since there is only overlap right here, 0, 0, so it's gonna be just 1, right? Multiply x of k, multiply all of this times all of that. There's only overlap at index 0, so you're gonna end up with 1. Now for y1, you're gonna end up with, at index 0, you're gonna end up with 1 times 1, which is gonna give you 1, plus the index 1, you're gonna end up with 2 times 1, which is going to give you 2, right? So that's equal to 3. Now y2 is equal to, for the same reasoning, 1 plus 2, but now since we shifted to the right by 1, plus 1, right? For 2, it's going to be 0, you get a 1, 1, you get 2 times 1, so you get 2, and then at 2, you get 1 times 1, which is 1, so 1 plus 2 plus 1, which is just going to be equal to 4, so you can already start seeing that we're going to end up with the same answer. y3, by the same reason, is just 2 plus 1, is 3. And then just continue with the pattern, right? Let's see what's going on. You can just keep flipping to the right in your head and seeing which ones are going to overlap. If you do that, you're going to see that y4, it's going to be equal to 1. And then y5 will be equal to 0. And then y6 is equal to 0. So hey, that's nice, because now let's go ahead and plot this. So step 4 is actually drawing it. So let's draw y of n. So what's our answer after doing this? And you see, I'm not very good at doing this because I never remember, because it's not too intuitive, but some people are actually pretty fast. They can flip and shift in their head, so they can figure it out very, very fast. And so for them, this is the way to go. So if we draw this, you're going to end up with the following. which is exactly the same answer we got before. And so again, we prove another way of finding the convolution, finding the output of a linear time invariant system using convolution. A little bit less intuitive, but it works. And if you get very mechanic at it, you can make it pretty fast. So now we'll go over the mathematical approach, which there is just a little intuition, not very much at all. So again, the steps. And this kind of relies a little on your bag of mathematical tricks. If you're pretty good at changing the limits of sums and simplifying mathematical expressions, then you're gonna like this. So this is just gonna be choose the easiest. And then again, remember we said that h of k and x of k, so h of prime of k and x prime of k. So remember, if you have x of n and h of n, then sometimes it's easiest to flip x of n. So that's what you're gonna do. You're gonna name it h prime of k, and then you're gonna name h of n x prime of k, right? So you're gonna just flip them in the equation. So now step 2 is just gonna be plugging into the convolution equation and manipulating the terms. And then step 3 is the big question. I mean, can you change the limits of the sum, make it look like something you can actually simplify? And those are the little, they call it like the mathematical tricks. Just look at the equation and you realize, hey, you can change this to something else. And then again, you see the pattern. So this is identify the behavior. So I mean, if you can see the pattern, then you can simplify. If you can identify the behavior, you can simplify. Or you can use some properties to transform the sum into something. Makes more sense. Okay. So we're gonna take the same example we have just been working with. So it's gonna be, but now we're gonna take it with the mathematical approach. So we're gonna have x of n, which in this case is gonna be, actually no, we're gonna take an example that is just a little bit, that will come out nice at the end. So we'll take just a simple example it's a proof of concept. So we got x of n is equal to just the unit step function starting at 0, and the impulse response is just gonna be the Dirac delta, or the impulse at 0 and then delayed by 1. So remember, step 1 was rewrite in terms of the easiest one to flip and shift. X prime of k. So we're gonna say that x of k. So you see, in this case, it is easiest to flip h. It is easiest to flip x. I'm sorry. And so that's the one that we're gonna declare as h prime of k. So for x prime of k, we're gonna just make it be equal to h. Alright, so it's not too bad. And then h prime n minus k. That's the one that's gonna be easiest to flip in the equation. We're gonna make it be u of n minus k. So now go over to step 2, which is gonna be plugged into the convolution equation. It's not good. There we go. So I'm plugging in, doing that with the following. Okay, now plug it in. Okay, so put negative infinity to infinity. Alright, now that we have that, then we're gonna go into step 3. Remember what step 3 was? Trying to modify the limits of some. So we can note that due to the unit step u of n minus k, this expression is only going to be 1 for n minus k more or equal to 0, or k less or equal to n. So we can modify the limits. So let's write that. Due to the u of n minus k term, and therefore we can modify the limits, which we will do in the next page. And so now our expression is going to be simply just given by k, still from negative infinity, but now we go up to n. Okay, and that can further be broken up. Alright, so now if you identify this is just an accumulator for both systems, where for this one you're gonna have it's starting at 0 and it's gonna be 1. You're gonna have 1 at 0 and it's gonna be 1 forever after, right? Because everything else is 0, right? The unit step is just that one. So if you add that 1 and you keep going all the way up to n, it's just gonna be 1, right? So that's what you're gonna do for that one. And then for this one, it's gonna be the same thing, but now it's gonna be delayed by 1. So it's not gonna start at 0, but it's gonna start at 1. And then forever after it's gonna be a 1, all the way up to n. Correct. So yeah. They are just accumulators, that's what they call. So therefore, y of n, it's gonna be, and what is this, right? This is just a unit step. And that's just a unit step. So that extends all the way. Minus u of n minus 1. And then what is this right here? Well, I mean, think about it, right? You have this thing starting at 0, there's the unit step going all the way up to infinity. And then for this one, you're gonna have the same thing, but now starting at 1 and then extending all the way up to infinity. Well, when you take the difference of that, you end up only with this guy right here. And so you end up with only that guy at 0. And what is that? Well, we're back with the with the impulse. You just have an impulse, right? And there is our answer. The answer for this problem. So you see, this requires a little bit of thinking here, and you see problems can get very complex later on, and then you have to change the limits, being able to see if the sum converges, and you can simplify it. Whereas if you apply the other methods, you could kind of get a more intuitive feel for what's happening. However, with some of, if the input or the impulse response is not finite, then basically the only choice you have is to apply the mathematical method, right? All right, so just some properties of convolution. I mean, this is not too important, but it might help you simplify a lot of things. Actually, it is pretty important, but it is pretty important if you want to rearrange things, move things around, make your life a lot easier in some of these problems. So you got associative, you got a distributive. So what is the associative one? Well, that is just the x of n convoluted, or convolve with y of n, convolve with c of n, that all equal to this x of n, y of n times c of n. That's all it is. And then for the distributive, it's just like that. That's equal to x of n, both so you see, and then the proofs for this you can find online. That's no big issue. And then you can see how they carry it. This is math. Yeah, so we just went over first an intuitive view of how convolution all works, you know, like the basic understanding of that. Then we went on to different techniques for making the computation a lot faster. And then so what I want to leave you with is that convolution is not that hard. Actually, it's not hard at all if you can understand it. And, you know, hopefully you did. So, thanks.